Okay, wake up. Sorry about the coffee. Coffee is very important to me. I don't know why the coffee service people didn't bring coffee yet.
No.
But I promise you, we'll be here by the break time. And Jason has a cup here. Should I have to share that? There's a sip for everybody. Okay, so thanks for all the questions yesterday. That was great. Please keep asking questions. Hopefully the practical sessions went well. Yeah? Good, great. Okay, so you'll see some more stuff today, and we'll continue. We have two surprises for you. So that's all I'm going to say. We'll see if you get one of them today. Coffee's not a surprise. Okay, so we have 4 great talks this morning. Bianca,
Haberl. This is really loud.
Happy. Okay. Stan Tozer, where'd you go? Back. And Jason Jeffries here. So we have 4 great talks on high pressure stuff. And that's it. Then the practicals this afternoon. Coffee break and lunch as usual. So again, please ask questions. And yes, sir.
Can you turn off the spotlights on?
Oh yeah, I'm sorry. Yeah, good point. Thank you. Wait, let me try it. That's different. Okay? That's good. Okay, any other questions before we begin? Okay, thank you. Bianca, please go ahead.
Can you all hear me? This seems very loud from down here, so.
Yeah, that's why.
Yeah. Oh, so thank you for organizing the school and for inviting me here to tell you a little bit about high pressure neutron scattering. And specifically, I want to talk about the complexities of doing these experiments and why we try to turn the various knobs to improve experiments, to enable new capabilities so that we can keep pushing the envelope. So just before I start, one question. Who has done any neutron scattering here? Oh, okay, that's surprisingly many, great. Okay, so before I start, I want to, of course, acknowledge my co-workers. There is the team that is involved with the snap beamline, that is our high-pressure diffractometer, and in pushing the diamond Enversal technology there, so you will hear a lot later about neutron diamond Enversals. Then we have, I'm collaborating. No.
I think if you just stand a bit this way, so you're not right in front of the speaker, there won't be so much feedback.
Oh, okay.
Sorry.
Am I stand up? No, that's okay. Does that work better? Yeah, okay, great. Then I'm working with a team on enabling multi-extreme conditions. So this means we are coupling pressure with something else, in this case, ultra-low temperature, so with a dilution fridge. Then I want to talk a little bit about inelastic scattering under pressure we are doing. So the development example I chose here was with the chemical spectroscopy team, so that's our basis and vision beamlines. And lastly, we are also pushing background reduction through development of collimators. So I'm working with our whole team there on making these things happen. I promise I will keep doing that, sorry. So just as a quick overview, I want to talk a little bit first about high pressure neutron scattering in terms of the general complexity, and which really boils down to the fact that we need very large samples, which is not the best thing if you want to do high pressure. And then I want to talk a little bit about the knobs we are turning to improve capabilities. So these are, of course, instrument and neutron sources, then the background reduction through collimation, before I then talk about a few of these examples where we are really pushing things lately, the megabar neutron diffraction, inelastic scattering, and these multi-extreme conditions. So I don't know who of you have been to Oak Ridge National Lab. We have two neutron sources. We have the spallation neutron source and we have the high flux isotope reactor. We are doing development at both these sources. So today I'm talking about the things we are doing there, but I do want to point out that these developments are really going on worldwide. There's a lot of push for more high pressure neutron capabilities. So this is really not an effort that's just limited to us. It's just since I'm talking, I'm picking our own examples. So let me get started with high pressure neutron scattering. So for those of you who have not used any neutrons, you may wonder why bother if I'm already telling you it's very complicated. So one reason is, of course, that neutrons scatter very differently to X-rays because they scatter off the nucleus rather than off the electrons. So your scattering cross-section is not dependent on the Z number. So you can have very interesting things like, for example, you can see a light element next to a heavy element. So in the realm of metal hydrides, it's very interesting. You could see hydrogen next to a lanthanum atom, for example. And then you can also play with isotopes and get isotopic contrast for further insight. Neutrons also carry a magnetic moment, so you can actually get information about the magnetic phase diagram. Of course, you can also do inelastic neutron scattering for some insight into dynamic correlations. Neutrons can penetrate quite what we consider heavy elements, so you can actually do scattering in something that's encased in lead. So that can be very useful for extreme environments. So there's many advantages and unique things you can do with neutron scattering. And if I were to talk about all the things you could do, I would eat the whole morning. So if you really want to learn more about neutron scattering from our past summer schools, we have some of the material now online thanks to COVID. So if you're interested, please check it out. You will recognize Efrain there as one of our summer school lecturers too. So just a brief overview, neutrons are usually generated by two methods for high pressure neutron scattering or any sort of scattering experiments. They're either made in a typical neutron reactor. So in Oak Ridge, we have the high flux isotope reactor, which we use for these purposes. Or they're made by a spallation neutron source, where you accelerate some protons, essentially, and you hit a target that then spoils out the neutrons. Both these processes are not as efficient as the photon generation at a synchrotron. So as a result, our flux is a lot lower, and that really drives a lot of the development and the things we do. So now to switch over to pressure, and this is the only formula I'm using. So as you all know, pressure is force over area. So if you think about it, if you use a very small area of, say, a micron diameter radius, you need very, very small load just to get to 10 GPa. So this is actually used for in point loading when you do indentation experiments, or also when people use it to induce phase transitions, where you need minuscule loads to get to relatively high pressures. Now, if you want to make larger volumes, you of course need something like a diamond anvil cell. And I don't know if you actually know that, but the diamond anvil cell was invented at NIST. Back then they had this major advantage that the FBI was confiscating diamonds for various reasons. And if you were a research or government entity and you had a legit use like research, you could get all these diamonds for free. So this is what enabled NIST to go ahead and really develop the diamond cell, because they had that free supply of diamonds and they broke a lot in the beginning. So if you're interested in the details, they have it actually on the website in this pamphlet. Are they actually getting the slides for these links? Okay, great. So yeah, there's a link there. And the pamphlet also states how the cell is still sitting in the museum. So very recently, I had reason to visit NIST, and I got to do a little trip to the museum to check. So the cell is still there. You can still see it up in the museum at NIST.
This is in Gaithersburg?
Yep, that's in Gaithersburg. Yeah, I know you're doing this too, but the museum is a little bit off track. But so For most high-pressure applications, these diamond anvil cells have really become the tool of choice, and stay tuned for the next talk where Adam will tell you all about how to use them, what they can do, and how to prepare them. So all I want to talk about a little bit is sort of the standard sample volumes and the load you need. So if you look at a normal diamond anvil cell, you would have a sample, let's say 80 microns across. So to get to just 10 GPa, all you need to apply is 30 kilograms. So, you can achieve that by tightening some screws. And these volumes are really sufficient for most applications, synchrotron X-ray diffraction or scattering, Raman, transport measurements. So this really is the tool of choice for the vast majority of pressure experiments. But when we now get to neutron scattering, as I mentioned, we need larger sample volumes. So the minimum size on most instruments would be 1 cubic millimeter, and most people will already call me crazy by just using such a small number. I mean, neutron beams are usually measured in inches. That's the size of the beam they will give you. So such a small sample volume doesn't typically work. So to get to a 1 cubic millimeter sample volume, you need to scale up your sample. So now to get to 10 GPa on a sample that can be contained in a diamond cell, you need 7 metric tons. So this means you're parking a big truck on your diamond cell. And this really means you need entirely different cells. You can't just have a little cell with screws that you tighten. And that really is the fundamental challenge of high-pressure neutron scattering. Neutrons prefer large samples, pressure, you need small samples, and we are trying to combine these two things. And the result of that is that we still use a large range of different cells that are specific to a given application. So just to give you a quick overview, the typical cells that are used in high-pressure neutron scattering are gas pressure cells. So these are cylindrical cells where a gas intensifier drives in a gas up to 10 kilobar. Actually, at NIST, they can do 10 kilobar. We can only do 7 kilobar. Then there is a whole range of cells that are specific for sands, where you have a different scattering geometry, so they're optimized for this. A typical cell is the so-called clamped cell, which are piston cylinder cells where you apply pressure in the press and then clamp in a nut. So this is why they're called clamp cells. These are the cells with the largest sample volume typically and are used worldwide across all neutron scattering facilities. The next breakthrough were then the so-called Paris-Edinburgh cells, named after where they were invented. So they are very big presses, 200-ton presses in some cases, where you have sufficient sample volume to do experiments up to 20 GPa at most reactor sources, at most neutron sources, really. We have been pushing the diamond anvil cells to achieve even higher pressures. And then there's also development in a whole range of other cells, like this palm cubic cell here, which is a multi-anvil cell that can be cooled. And with this large range of cells and applications, there's actually quite a large interest in by our users and our staff. So here's an overview of our 30-odd beamlines at SNS and Haifa. And 2/3 of them use pressure in some form. So if you're really interested in a specific experiment at one beamline, you can always come and talk to me. I'm here the whole week because I don't want to go now through each individual beamline and just bore you by telling you what they all do, especially given the coffee situation. So let me move on to how we are trying to push the envelope to improve things. And so the things we can work on is more neutron flux. If we have more neutrons, things become easier. To reduce the background from the cells, and then of course have new and different cells altogether. And these are really research areas that are going on everywhere, and all these components are being pushed. So I don't know if you are familiar with the number of neutron sources across the world. There's actually quite a large number of them everywhere. There's also new sources that are coming online, like the European spallation source. And as I mentioned earlier, most of them do high-pressure scattering, high-pressure neutron scattering. So our two places in the US, at Oak Ridge and at NIST, we do a lot of high-pressure neutron scattering. I'm sure you can ask Nick about some of the details of what they do at NIST.
I'd be happy to talk about it.
Since I'm talking so Oak-Ridge-centric, I don't want to exclude what you guys are doing. There's a lot of effort at the European sources, so that's why a lot of the development initially came from there, like the Paris-Edinburgh cell. But more and more, there's now also development in Asia-Pacific. So it's really something the worldwide community is investing in and building new instruments, building new dedicated instruments, building new cells. So here you also see a graph on how the flux of the various neutron sources has increased over the time. So right now we are up here with our pulsed sources. The ESS, the European Spallation Source, will come online in just a few years, so there's hope that they will push things further. And of course, we are also building a second target station in Oak Ridge, so there's a lot of opportunity to keep driving instrumentation to help with high-pressure neutron scattering experiments. Another aspect of the instrumentation is, of course, the instrument itself. If you have a dedicated high-pressure instrument, you can set it up differently than a standard diffractometer. You can make sure it's accessible. You can make sure you have a beam that is focused as much as possible. So here is an example of the SNAP beamline, our high-pressure diffractometer at the SNS, the Spallation Neutron Source, where this was me standing on top of the instrument looking down. So the beam comes out of the wall here, and then it hits here the pressure cell and scatters in both directions. So here you see a diamond anvil cell that is on the beamline. One key advantage there is that we can actually walk up to the beamline because we always add a little bit of cadmium, our preferred shielding material, here or there to improve any background features. So here is an example of why SNAP works well as a high-pressure diffractometer. It has a guide that forces the neutrons to arrive in a focus spot. So neutron optics are not as nice as electron optics or optics for photons, but we have some control to guide them to where we want them to arrive. So at that diffractometer, we have them in a 2 by 2 millimeter hotspot, which for neutron applications is an extremely small beam. As I mentioned earlier, a lot of beamlines have beams that are inch by inch. So this has been really helpful for high pressure applications because we have all the neutrons that we have at least arrive in a smaller spot. There have also been a lot of new instrument concepts. So here's a concept that was pitched for the second target station. It's not one of the instruments that was selected for the first round, but we are continuing to push it. So this was the Titan concept, which was meant to push generally an instrument for extreme conditions. And here's a simulation of a diamond anvil cell and the sample we would have in our typical neutron diamond cells at 150 GPa if this sample was an actual lanthanum hydride. So this is not something we can measure at the moment yet. We don't have that instrument. But if we can push the development, eventually we can really do 10-minute exposures and get a reasonable diffraction pattern at these pressures that are critical to the metal hydride community. Yes?
What goes into so what assumptions go into that simulation?
We used one of our neutron diamond cells with that can achieve 120 GPa. So we actually used the real sample volume that we had at 120 GPa.
I guess the main question is, you assume that it's like 100%?
Full, yes.
Yeah, okay.
Yeah, yes. So that is one big thing. We still probe the entire sample, not just a small component of it. So yes, we did assume that the entire sample would be filled of the lanthanum hydride. So yeah, just to sort of summarize this a little bit, as we are working on new neutron sources, we are working on focusing guides, new instrument concepts, and these developments will bring more capabilities for high pressure neutron scattering. So I don't want to get into the depth there, but I just wanted to give you a scope of the community is really pushing this and moving ahead there in various directions. So that brings me to the next chapter, which is reducing the background through collimation. So as I mentioned now a few times, we have a large beam, we have a small sample. We do not want to expose the sample environment, so the pressure cell to the beam. We only want to expose the sample. So typically what you do in most cases is you wrap everything you don't want exposed to the beam with cadmium. So here you see an example of a diamond anvil cell where all this gray stuff, with the exception of the anvils and the gasket here, is cadmium. So this already reduces the background a lot. But as your samples get smaller and smaller, your pressure cells, they also change in geometry as you apply pressure, so there's a limit to how much you can achieve with cadmium. Aside from the fact that the higher energies at a spallation neutron source will actually penetrate cadmium. It's not applicable everywhere. So we have started, yes.
It's a technical question, I suppose, but how about the non-neutron radiation? You know, basically all of the pump gamma. Does that require additional shielding?
So at SNAP, the high pressure diffractometer, we would not use cadmium in the incident beam because they have anger cameras, so they light up like Christmas trees. So it's really more something we use in the scattered beam. But for a lot of the single crystal diffractometers, or also at HIFA and some of the inelastic instruments, it works well. But yes, it has its limits, which is really why we started playing with more sophisticated incident beam and radial collimation based on boron. So we got quite involved with 3D printing various boron collimators. So the advantage of 3D printing is, of course, that you can make very complex shapes. You can also make quite small things. Boron is not something that is easily machined, but it is the element that absorbs neutrons best. So this is really what we want to use. So here are some of our typical collimators that we are using now. These little snout things here is what we use with the Paris-Edinburgh cell. So this front bit here is what points at the sample to make sure we only illuminate the sample and nothing of the pressure cell. And then these ones here are more complex shapes we actually printed for our diamond anvil cells for single crystal applications. Because there you want to rotate the cell in the beam, so you need a large sort of aperture where you can rotate around. So this is what we call colloquially incident beam collimation. It's technically not collimation, it's very sophisticated shielding, but it's been really crucial for high pressure experiments to make sure we only illuminate the sample and as little of everything else as possible. We of course also play with radial collimation. So this is collimation of the scattered beam, where you can use geometric constraints to select that only the scatter from your sample arrives at the detector and not from the cell. So here's a typical radial collimator, or for X-ray experts, this is akin to solar slits, for a gas pressure cell. So this is a cylindrical pressure cell, which works very well on the SNAP beam line. So here you see the aluminum peak. This is the cell, that cell peak, that once you apply the collimator, it's essentially removed. So these things, of course, are very critical also to reduce unwanted scatter and ensure you only see the samples that don't scatter as well often. So we have been taking that to a next step to optimize these scattered beam collimators through McVine. So this is Monte Carlo ray tracing, where you can actually simulate the instrument, the sample environment, so the pressure cell you put in the beam, and the scattered geometry to really optimize what arrives at the detector. I don't want to talk through that in detail. I just want to show you this is a very complex optimization. So this is why it needs to be done computer driven. You would not be doing that manually. And so we printed just a few test pieces where, again, here you see the example of the cell, so the scatter you don't want without the collimator, and how much is reduced when the collimator is added. So these things are complex and they're still work in progress, but they do add a lot. We have also been extending that to the very small sample volumes that we use in the diamond anvil cell. So here you see a model that went into McVine, that simulation program. And then we 3D printed collimators from B4C. So they were getting very, very complex because 3D printing with B4C has a lot of limitations in what you can actually do. So our designs are getting more complex, blades are alternating, but overall the proof of principle does seem to suggest that here when you look at so this one was normalized, so now a higher sample scatter means that the collimation actually reduced the sample environment. So yes, these things work. They're still work in progress, but I think future instruments will incorporate more and more components like that. So yes, just to summarize this again, we focus a lot on incident beam collimation to make sure we only illuminate the sample. We also work on radial collimation or scattered beam collimation to further improve these things. And of course, these are all critical for high pressure neutron scattering, since our samples are small, sample environments are big. So the signal from your sample can be easily lost in the background. And so finally with this, I want to get to some, yes, Dan.
Okay. What limits the flux? And the line for progress looks rather flat. Are you guys at first generation, second, as far as?
So once you in a way, that plot was only showing the neutron source, but you really want to look at the instrument. So for example, now there's a lot of development in moderators. So once you can have a smaller moderator, you can actually have a smaller beam. So if you have the same amount of neutrons arrive somewhere, but then I focus them in the tiny beam versus a large beam, I still have a lot more flux on the sample. So this is really where the STS is sort of focusing on to have more, to have new moderator and guide technology to actually achieve that higher flux. But if we want to talk about all the details of neutron sources, maybe better to do that later. Does it answer your question a little bit? I mean, the physics of how neutrons are generated just sort of limits us. It's a very different process to how we produce photons at a synchrotron. Unfortunately, I would really like to have a neutron synchrotron. Okay, so now let's talk a little bit about high pressure cells. I want to actually start with inelastic neutron scattering to work my way up in sort of the highest pressures. And inelastic scattering has a lot of advantages in the information you can access. You can probe information you cannot probe with diffraction, of course. But because it's an inelastic process, your flux, basically you need an even larger sample volume. So the usual guideline is people tell you need a sample volume that's 100 times as big. So again, for high pressure neutron scattering, this is not an ideal scenario. And so that's the reason why the standard cell for inelastic neutron scattering is still largely the clamped cell. But recently, there's also been development to push the inelastic neutron scattering to the Paris-Edinburgh cell. So these are these large presses that can achieve up to 20 GPa, which is what I want to focus on. But before I get to that, I do want to briefly show you some of the things we are developing for the clamped cell. So here, just for those of you who have never seen them, these are these piston cylinder cells hanging on a stick. They're sort of that long. They are pressurized inside a press. So this is the nut you turn once you have applied the load. And here you see the individual components. So this here is a Teflon cup where you can put in your sample together with a pressure medium. And then these here are these carbide pistons that are used to apply the pressure essentially to the sample. Now, one thing that is tricky with these cells is determining the pressure because you don't have optical access. So that's something we started using recently in Oak Ridge. We modified one of these pistons here with a diamond window at the end so that you can actually get in a laser, which lets you measure the pressure with ruby fluorescence. And I believe Adam will tell you later all about ruby fluorescence. So this has been very useful in a recent experiment where we realized that how you clamp affects the pressure a lot. So typically you would use a so-called pressure load curve as a guideline. So you calculate the nominal pressure just by pressure is force over area. So this here is that gray curve. Then you would assume that you lose some pressure to friction, so say 10%. So then this is what you would assume as the pressure you have on your sample. But when we measured it with ruby, the first pressure point was spot on, but then the second one, we were a lot lower. So then we realized it wasn't clamped sufficiently, even though we thought we were at the nominal pressure. So when we clamped it again, we got to a lot higher pressure. So these are just sort of these caveats to be aware of, and where it was really useful to have this offline pressure capability, because once you put it on the neutron beam line and you've already used 2 or 3 days of beam time just to then realize your pressure was not correct, can be non-ideal. I believe there's going to be a talk later on experiments in piston cylinder cells, so I didn't want to get too much more into those. I just wanted to point out that even with these cells, there's a lot of development and things that can be pushed. So now this brings me to the Paris-Edinburgh cell, which the first experiment we used it for inelastic neutron scattering was actually on the basis beamline, which uses quasi-elastic neutron scattering. We did not come up with this idea ourselves. This is actually something we modeled after work Stefan Klotz did in France, because they realized that the gaskets give you the advantage for, so Quenz likes to use annular samples, and the Paris-Edinburgh cells actually have a gasket shape that allows very easily for annular samples. So typically the sample would be here in the center, but for the Quenz we put it here in that ring. So this was something, yes, the sample was in here. Our first experiment was something hydrogenated, which why we wanted the sample very thin. So here you see the setup of that Paris-Edinburgh press. So this is that's a smaller one. That's a 150-ton press. On that long contraption, this is how it went down into the basis beamline. So most neutron beamlines, unlike a synchrotron beamline, you don't walk up to it. They're actually down in tanks so that things can be evacuated and you can reduce backgrounds. Additionally, these cells, they can blow out, which can be quite violent. So we added a blast shield, which actually is a modified pot. Really, this was a pot from McMaster. So these are all things that can be optimized because obviously they contribute to background. Yes.
What are the materials here?
Of the pot or the cell? The pot is aluminum. So the cell itself, this here is all steel. The anvils are in this experiment are cubic boron nitride, and the gasket was copper beryllium. But typically a Paris-Edinburgh cell would use Ticer gaskets because they are using that isotopic mix where you have a null scattering gasket without any Bragg peaks. At ISIS, they have some of these Paris-Edinburgh cells that are entirely made from copper beryllium. So they exist, but we don't have those. So now I know this talk is more about telling you about what we can do with high pressure neutron scattering rather than get into some applications. But I just wanted to briefly introduce this here because it sort of highlights how we were coupling a couple of two instruments to do these experiments. So the example we were working on was barium hydride. A PhD student, Eric from UTK, was very interested in that, so he was really pushing that project. So barium hydride is an interesting material for hydrogen storage, and it has two polymorphs that you can access with pressure, but also with temperature, that have very interesting behaviors. So the idea was really, can we understand that with Quenz? Because Quenz looks at a small energy transfer, and so it gives you some insight into these behaviors and hydrogen jumps. So this here is the previous high pressure work that sort of spiked our neutron scattering experiment. There were some observations from impedance spectroscopy that showed that the high pressure polymorph may actually be advantageous. So this is something we were trying to understand and where we thought we could get to that pressure regime, and it was a sort of good opportunity to push this capability and see what we can do. So first things first, we need to make sure we actually get to the pressure we are interested in. When you are using a Paris-Edinburgh cell, you again don't have any optical access to measure pressure. So the only way you can first estimate the pressure given on some pressure load curves that have been established for other samples, but then you really need to use diffraction to measure the actual pressure based on your sample. And I think Adam will also talk about diffraction standards and things like that later, so you'll hear more about equation of states then. So when we started with this project, we first made a deuterated version, which we measured on our high pressure diffractometer to understand the high pressure behavior, where we noticed that because this sample has to be loaded without a pressure medium to avoid any unwanted reactions, we noticed that there is quite a large regime where you have coexistence of both these phases. So for the Quenz experiments, we had to be careful that we get to a high enough pressure, which is actually higher than what we saw from all these previous works, to make sure that we actually probe just the high pressure polymorph. So then once we understood how our particular sample in these large volumes behaves under pressure, we replicated this experiment on SNAP using the exact same gasket and the exact same geometry to again measure the pressure load curve for the specific setup that would go then on the Quenz beamline. And then afterwards, we replicated the experiment on the basis instrument where you cannot get the pressure, but of course where you get the information you want to get. So here in this particular case, this is the result. If you've never seen Quenz data, basically the information you are interested in is hidden here in the width of these tails. And so this is when you then start with sophisticated analysis and models to extract the information you are after. And so in this case, we found that the residence time increased quite a bit once we got out of that regime where we had still a mixed phase and got to the pure hexagonal polymorph. But overall, we found that for real quantitative analysis, we wanted larger sample volumes or longer count times. So the Quenz experts were sure they analyzed this correctly, but to really get the full information you can typically get from an experiment, yes.
Other than what? How long did that take?
We tried it again with 24-hour exposures, but then there was an issue with the source during that experiment.
That doesn't sound like that's not like an absurdly long time.
No, it's not absurd. I mean, these experiments, I think we ran for 8 hours, 8 to 12 hours. It's not weeks. It's sort of just at the cusp of what we think we, could do. And that also brings me to a point I haven't mentioned before, that at the SNS, we are currently down for a major upgrade. We are getting a proton power upgrade that will actually get us more flux. So just getting 40% more flux may actually help to make these experiments more feasible. So this is something we will revisit after the proton power upgrade. So please stay tuned on some updates and what's becoming available in the user program. Additionally, we have also been able to use that whole setup on other beamlines. I've been taking it to the ARCS beamline, one of our inelastic neutron scattering spectrometers. But I will talk about these examples on Friday in my workshop talk.
The cell was the Paris cell? That was developed specifically for neutron scattering?
Yes. And it's also a good cell for synthesis. People do use it for synthesis because you can get to 20 GPa on a relative large sample volume. So yes, it was developed for neutron scattering, but it's sort of, been expanded in its use. Okay, so that gets me to the back to diffraction, specifically megabar neutron diffraction. So this is diffraction above 100 GPa. So far we've really been talking about relatively low pressures, but if you want to start playing with things like metal hydrides, you really need higher pressures. So you need essentially 3 things. You need a neutron diffractometer that can be used for these type experiments, and with SNAP, we've gone quite a sort of, when recent upgrades on the beamline, we have gone quite a far way in doing that. You also need the necessary tools for data analysis, which can get very complex, so I'll talk a little bit about that on Friday. And finally, you need, of course, a diamond cell that can give you that pressure, but still have the sample volume you need for neutron scattering. So that's the bit I want to talk about now. So neutron diamond anvil cells have been developed all over the world for quite some time. So the initial work by Igor Goncharenko did a lot of really nice work on hydrogen, various quantum materials in France. So if you're interested in that, there's quite a large body of work. These gem cells were limited to 40 GPa or thereabouts. There's also been recently quite a push in Germany where they are developing diamond anvil cells that they can couple with low temperature, so they are all made from copper beryllium. But currently their source is down, so they are not pushing that further. And then there has also been quite some efforts at JPAC in Japan, where they're using very expensive nanocrystalline diamonds and then have built a little diamond cell that fits into the Paris Edinburgh press, where they achieved almost 100 GPa. So yeah, I just want to highlight, it's not just us working on this. This is really, if we want to get to the pressures we want, the whole community wants to contribute there. So at Oak Ridge, this effort started well over 10 years ago. Actually, it started at the geophysical lab here in DC, which had a huge energy center focused on high pressure. And so they were really pushing these neutron diamond anvil cells for the SNS. And the first iteration is, I don't know if you recognize this, this is a normal panoramic diamond cell that is also used at the synchrotron. And so they just built a big press where they put the cell in so they could get to these loads I mentioned earlier and actually got to quite high pressures. So here is their record pressure on that cell, which actually did get to 94 GPa, but that cell had severe drawbacks. So first, this here's the diamond. These were the largest natural diamonds they could afford at the time. So to stabilize them, they needed this elaborate seed setup, which was just as expensive as the diamond. And every experiment saw the seed and the diamond broken. So it's not a very useful thing to use in the user program. Additionally, this, because with neutron scattering, the incident beam comes in here and then you scatter out that way. So this cell severely restricted the scattering aperture so that you could basically, it was great to study ice. Other materials, not so much. Yes.
All right. What would be the disadvantage, or is it possible to, I mean, the areas are huge, right, for your sample. What if you had an array of diamond cells with smaller volumes that could reach higher pressures, and you would have essentially the same effective volume of sample? And you just put it all, your beam's big, so you put all of that into your beam and go.
So for our scattering geometry, if this is the cell, we come in through the anvil and we scatter out to the side, not to the front. So you can't just put them.
Right.
I mean, the data analysis would become a nightmare. I don't think you could analyze that. Because you would need to take the attenuation of the first cell of the two diamonds plus the third diamond into effect on what arrives in, as incident beam and on the second sample, and then this would just go up in complexity.
You just put them all in a row. Small diamond cells, put them all in a row, shoot the beam straight out.
So I'm not sure. So you, if I have a diamond cell, and put the other one.
I've got my beam and I'm just putting diamond cells across the way, right? You want to put them one front to back. I'm saying put them side to side.
And then I'm exposing the whole cell.
It's a diamond cell, true. Right?
No, but this is massive background, right? Then I look at the tiny sample and all the.
It'll work. No.
Yeah, and then you would have to make sure that each cell has the exact same pressure, exact same conditions.
Well, it's within the same pressure gradient as you had in a large cell. A sample that large has massive pressure.
Oh, and it's some. I would need to think about it. I doubt it would work, but I would need to think about it in a bit more detail. Because, I mean, basically you would need to design a completely different instrument that has like a whole range of focus beams that hit all these pressure cells. Otherwise, you're just gonna throw away the majority of your beam hitting.
Pressure cells large, right? I'm assuming small. You could have a much smaller pressure cell for those smaller samples.
Yes, but my current neutron beam is 2 millimeters, so I cannot put two cells next to each other, hit 2 millimeter. So if I now stop from focusing that and I have the neutron spread over a larger area, so I can capture 3 cells in there, I'm basically going to wash out the focusing. So I don't think I would actually get more neutrons on the larger number of samples than I would having all the neutrons focused into one sample. But it may be something to draw up and think about. Okay, so after that first cell, that first megabar cell that was useful for ice, but not so much other science, we were very lucky and that CVD envers came along, which allowed us to use a lot larger diamond envers cells, use a lot larger sample volumes because we could now afford larger diamonds. So it really just came down to the diamond price in this case. So this was the next iteration of the diamond cell where we now had quite a large Q range. So this was now applicable to a lot wider science than just to ice. Pressures were initially sort of limited to 45 GPa on reasonably sized samples. So this is what was used for quite some time then across SNAP in various diamond enver cell experiments. So here you see a few more examples there. So these here are these CVD envers. They were all bowler cut conical envers so that we could actually get to the loads without the diamonds breaking. We used some pre-machined gaskets to give a little bit more radial support on the top of the anvil. That again helped with the stability. And the pressure record we managed with these cells was a little bit over 60 GPa on yet again ice, but these were fully refined data that we were able to get at these pressures. But we did find there was limitations. We never managed to get much higher than these 60 GPa. So the breakthrough came really more recently during the pandemic. There were several advantages. The SNAP beamline had a few upgrades that really helped with better detectors and a better guide. Additionally, Riley designed a whole new set of diamond enver cells, which are based actually on these roller bearings here. So when you have a diamond enver cell, anytime you apply load and your envers align while you misalign while you apply the load, the envers break. Now, when you are applying 7 tons or 10 tons, this gets even more severe. So our biggest problem was really have cells machined to the perfection we needed so that we wouldn't misalign the envers as we are compressing. And this is really what was addressed with these roller bearings. So now the piston, so this is where we push on, is guided into the cell with these roller bearings, and we don't have any misalignment any longer. So this has really been the breakthrough that allowed us to get to 100 GPa now. So here I just want to show briefly, these are the data we get at 100 GPa. I mean, we are cheating a little. We are using nickel, which scatters extremely well. But then these were only, these were only 2-hour runs. So it's not like we were counting for massively long times. And Malcolm Guthrie invested a lot of time in analyzing the data and refining them. So here at 100 GPa, you can still do a full quantitative read weld because it's not sufficient to just have a cell that gets you to that pressure. You also need to be able to analyze the data so you actually get out the crystallographic information you want. So yes, to summarize this part is a lot of effort has gone into this development. It's still ongoing. We can now do 100 GPa at room temperature. At lower temperatures, this has been more limited because we have to change the gasket material, which has not been cooperating all that well. But in general, these cells are available in the user program. So if anyone has any questions or ideas, please come and talk to us. And I will also introduce a few more science examples where we've actually used these cells on Friday. So now I just want to use 2 more minutes, if I can, to talk about coupling some of our diamond enver cells with ultra-low temperatures. Ultra-low temperatures in this context, I mean anything below 2 Kelvin or thereabouts. These are regimes where it is very difficult to do high pressure X-ray scattering because to get your beam into the diamond anvil cell at the synchrotron, you need to have reasonably high energy focused beam, so you have a lot of beam heating. So usually their temperatures are really limited to 5 Kelvin. So with neutron scattering, you have less flux, so you actually have less beam heating. So neutron scattering has been very good at ultra low temperatures and actually at coupling diverse extreme environments like magnets or clamp cells with dilution refrigerators, for example. So here we did not use our new megabar diamond cell. We actually used a previous iteration that was made from copper beryllium. So this was a cell that was developed for inelastic neutron scattering actually on the vision spectrometer, but was mainly used then for single crystal diffraction across the instrument suite at various single crystal diffractometers at SNS and HIFO. The advantage is it has a very large scattering aperture. It uses Versimex anvils, so this is a polycrystalline diamond that's actually quite cheap. So you can also get it in quite sort of larger volumes, and you can use very large QLIDs to increase your sample size. So this cell also has a small spring here added that adds temperature stability, because of course as you cool things, things expand, things shrink, or when you change temperature. And you do not want any of these changes affecting your pressure. So these ones here have been quite stable on cooling to 5 Kelvin. For these cells, we also have some pressure load curves that we can use as a guideline. I would not say this is what your final pressure is, but you want to have a rough idea of what you are shooting for before you actually start pressurizing. So we chose a sample just based on, it was something we wanted to trial this with, where we knew there is a magnetic phase transition, where we see some magnetic peaks. So we pressurized, we loaded this sample into our diamond anvil cell. We used, as pressure medium, we used deuterated glycerin, which has the advantage that it doesn't evaporate that fast, so you can actually fine-tune the alignment of your sample while the liquid is already in there. And then we applied a load of 5 tons, which we expected would get us to around 4.5 GPa. So here is an image of the sample inside that pressure cell. So that gasket chamber here is 3 millimeters diameter. And then here, all these single crystal spots are the sample as we see them on the SNAP diffractometer on the beamline. So after that, the cell was pressurized, and then we added it to the dilution refrigerator, which was actually several experiments until we figured out how we do that so that we still see something. Because as you're cooling, the fridge moves, or the sample moves out of the beam. So there were several iterations and learning experience involved with that. But overall, another interesting thing we learned was the initial collimator was this 3D printed collimator I showed you earlier, which is made from boron. And with this setup, we actually see some beam heating. Without the cell, without beam on, you can cool that cell to 50 millikelvin. With beam on, we were only able to get to 200 millikelvin. And the current scenario is that the gammas that come out of the boron when it's hit by the beam hit the cell and then warm it up. So for the second experiment, we used a smaller B4C collimator, which allowed us to get down to 170 millikelvin. So, but this is something we are still working on to improve that beam heating issue that now also does exist for neutron scattering. So this is very recent work and analysis is still in progress, yes?
Where was the temperature measured?
On the deck body. We did some, on the beamline it was measured on the deck body. We did several offline tests beforehand where they measured it between the anvils and on the deck body, and there was, I think, 5 millikelvin difference. So yeah, here you see some of the diffraction data as we got them on the SNAP beamline. So here, based on one of the diffraction peaks, we think that the pressure can be estimated to 6 GPa. but we are still revisiting this because this is just based on one peak, and obviously you do want to use more than just one peak to get the pressure. But here's just an example of how the background situation gets worse once we added the dilution refrigerator. But what is the really exciting point here is this peak, because this is actually a magnetic peak. So we were able to see a magnetic peak at 5 to 6 GPa and 170 millikelvin. So we are very excited that this is actually possible. And so, as I said, the detailed analysis is still in process. So here is the intensity or evolution of that magnetic peak. It does disappear as we are warming up, so it is a true sample magnetic peak. So yes, we are very excited about that it was actually possible to see magnetic peaks at these conditions. So to just briefly summarize this is something where there's still a lot of experimental constraints, but if someone has a great idea for a simple experiment, we would be happy to talk to you about that and see what is possible and if we could apply that. So finally, just to wrap up, if you are now interested in coming to Oak Ridge for some neutron scattering, or if you simply want to learn more about neutron scattering, the applications for our yearly National School on X-ray and neutron scatterings are open, so please do apply. It is a great school. And we also have the proposal deadline come up for SNS and HIFER experiments at the end of February. So if you have any ideas, then of course come and talk to any of us. And so in conclusion, I hope I was able to show you that high pressure neutron scattering can be very useful, it can be very interesting. It is also very complex. We are continuing to push the capabilities, we are continuing to push the pressure and temperature envelope, and there's really a large community sort of involved with making all this possible. So of course we are also very excited to share with anyone who's interested in doing any of those experiments. With that, I thank you for listening.
And just to reiterate, the school is really excellent, so if you have a chance, it's a 1 week.
It's 2 weeks, yes. It's 1 week at Argonne, where you learn about X-ray scattering, and 1 week in Oak Ridge, where you learn about neutron scattering.
Okay, questions, please.
I think everyone needs coffee.
Students only. I haven't heard a student question yet. Pressure's on. Yes?
What has been your favorite experiment that you've done at SNAP?
So my favorite experiment was actually pressurizing graphite. So we'll talk about that on Friday, because everything worked perfectly, the loading worked perfectly, everything behaved as we expected it, and then the graphite did something rather unexpected. So that was fun to see.
How long have you done high pressure neutron scattering?
About 10 years. So, or maybe 11 years. So my background was not in high pressure neutron scattering. I was sort of in materials synthesis and trying to understand the high pressure behavior of various silicon and germanium phases. And one thing we found was that hydrogen was affecting how some of our precursors behaved. So the high pressure behavior changed. We needed to know what the hydrogen was doing, and there was the path to neutrons.
Yes.
What's the principle using guiding the neutrons? Guiding the neutrons?
What is the principle we use to guide the neutrons?
Oh, what's the principle? Basically, a lot of the things you design inside the guide are based on geometry. So you're using some materials that sort of reflect the neutrons, and you design a geometric design that gets them where they're meant to be. So these things are also now quite advanced simulations. It's not something any longer you just design by hand.
Yeah.
Well, so up to 10 GPA, I think with the Paris-Edinburgh cell, you can now do inelastic scattering. I mean, it will always depend on the sample, it depends on the science question, it depends on whether you are happy with room temperature, if you want to add some other condition, but yes, there's some possibilities, and everything up to 2 GPA, what can be done in the clamp cell is really quite routine for inelastic neutron scattering. Well, as routine as any pressure experiment is.
Yeah, John, will you do any kind of multimodal experiment, like where you're measuring transport at the same time as you're doing your neutron scattering experiments?
Unfortunately not. This is something we would really like to push on SNAP eventually, that we can do transport measurement on the beamline. Because I mean, obviously it could save a lot of time, right? When we know, okay, now we are definitely in the state where we want to be, and this is when we do our 10-hour neutron collection. So yes, it's something we are interested in, but it's not a capability we have yet.
What limits that?
That our time? No, this is simply our time. There's only so much we can do with the resources and people we have. So if anyone wants to come to Oak Ridge and start playing with that, I'm all ears. We do have an outage right now, so there is some scope to play with things. So yeah, currently we are installing a Raman spectrometer on the beamline. So at the moment we have UV fluorescence to measure the pressure, but this is now being upgraded to Raman. So it's a sort of first step to add some more capabilities beyond just the diffraction.
Any final questions? Okay, thank you very much.
Wow. That sounds like I'm giving you all just things to explain.